Hello everyone, my name is Ayça Çayönü. I'm from the Electrical and Electronics Engineering Department, and I'm from the Physics 102 Section 11. My experiment looks at the internal resistance of a real 9-volt battery and how it affects the terminal voltage and power delivered to a load. An ideal battery supplies constant voltage no matter the current. Real batteries don't. Internal resistance causes a voltage drop whenever current flows, and the goal here was to measure that effect directly. In theory, a real battery follows the equation V equals epsilon minus I times R. V is the terminal voltage, epsilon is the EMF, I is the current, and R is the internal resistance. The relationship is straightforward. More current means a larger drop across R, which means lower terminal voltage at the output. Current is found using Ohm's law, and load power is calculated as P equals V times I. The setup was a 9-volt battery, a breadboard, and several resistors. Each resistor was connected across the battery one at a time, and I measured the terminal voltage with a digital multimeter. The open circuit voltage came out to be 9.64 volts. From there, I tested resistance values from 10 kilo ohms down to 22 ohms, taking each reading quickly to keep battery discharge from affecting the results. Using the measured voltages and known resistances, I calculated current and power for each data point. The pattern held throughout: lower resistance, higher current, lower terminal voltage. At high resistances, the voltage barely moved. The current was too small to cause a noticeable drop. At 82, 47, and 22 ohms, the drop became clearly visible in the numbers. Plotting the terminal voltage against current gave a straight line, which matches the theoretical model. The best fit equation can be seen on the screen. The slope is the internal resistance, and it is about 2.9 ohms. The intercept represents the EMF and sits close to the open circuit voltage measured at the start. R squared was 0.986, so the linear fit is strong. A second graph plotted power against resistance. Power increased as resistance decreased, driven by the higher current. The maximum power transfer point was not reached. Getting there requires very low resistance values, which produce high currents, significant heating, and less reliable readings. These factors also introduce some uncertainty at the lower end of the data range. The experiment confirms that internal resistance is real and measurable, with a direct effect on terminal voltage and delivered power. The data fits the theoretical model well and gives a concrete picture of how a battery behaves under different load conditions. Thank you for listening to me.